Hi everyone, my name is Michael Lampis and I will talk to you about minimum stable cut and tree width. Let us begin by defining the problem. We're given an undirected edge-weighted graph and we're asked to produce a cut, so a partition of the vertices into two sets, which for this talk will be red and blue vertices. A typical problem in this area is max cut. We're given such a graph and we're asked to produce such a partition which maximizes the total weight of cut edges, so the total weight of edges which have endpoints with distinct colors. For this talk, we're going to be interested in cuts that have an extra property of stability. So what does it mean that a cut is stable? It means that every vertex has the weighted majority of its neighbors on the other side. Or in other words, no vertex can unilaterally increase its incident cut weight by changing sides. In this particular example, we have a configuration that is not stable, because the vertex on the top right can increase its cut by flipping sides. Now you can observe that adding this stability requirement to max cut does not really change the problem, because if a vertex is unstable, that means we have a non-maximum cut. So the maximum cut is always stable. However, in this talk we're going to be interested in the converse problem. We're looking for a stable configuration which is a minimum cut, so that cuts the minimum possible weight without violating the constraint that every vertex should have the majority of its incident weight on the other side. One possible motivation for this problem comes from algorithmic game theory. We can imagine the vertices as selfish agents which are trying to maximize the weight of their incident cut. In this formulation, what we defined in the previous slide as a stable solution corresponds exactly to a pure Nash equilibrium of the cut game. So the question we're asking is essentially what is the price of anarchy of this game? So what is the relationship between the minimum stable cut and the maximum cut of the input graph? Now it is known that in the worst case, the ratio between these two values could be as large as 2, because a stable solution will always cut at least half of all the edges, and also because of the example that we had in the previous slide, where the minimum stable solution was cutting exactly one half of the edges. However, what we're interested in here is not a general bound, but a bound for a given specific instance. Another motivation for this problem comes from local search. We can view stable solutions as local optima for the naive local search algorithm, which at every step finds a vertex such that flipping that vertex can increase the size of the cut. Now, the corresponding problem in local search is called local max cut, and it's actually a very hard problem. So producing a stable solution is a prototypical problem that is complete for the class PLS. So given this information, and given also that in this talk we're interested in finding the minimum stable solution, not just any stable solution, it is natural to expect that minimum stable cut is going to turn out to be an intractable problem. So what is this talk about? Since we suspect that this problem is going to be hard, we're going to take the point of view of parameterized complexity. So we're going to try to exploit some structure in the input instance, and the two structural parameters that we're going to rely on are arguably two of the most standard such parameters, the maximum degree of the input graph and the tree width, which measures how tree-like the input graph is. In the first part of this talk, we're going to confirm the intuition that minimum stable cut is a hard problem, and in fact we will show that these two parameters are unable to help us solve it, because the problem remains NP hard when the maximum degree is constant or when the input graph is a tree. Nevertheless, in the second part of this talk, we are going to be able to give a couple of simple algorithms which are able to work around these barriers. One of them exploits the fact that the hardness for tree width only actually gives weak NP completeness, so we will be able to give a pseudo-polynomial time when the input instance has constant tree width. And the second algorithm will be FPT when we combine the two parameters, so when we assume that both tree width and the maximum degree have small values. Unfortunately, both of these algorithms have disappointing running times, so the main technical result of this talk will be a lower bound argument based on the exponential time hypothesis, which justifies that this cannot be avoided and that these running times are necessary. The paper also contains a couple of other results regarding almost stable solutions, and also unweighted instances where the problem doesn't get slightly easier, but we will not have time to cover this in this video. Let us now take a look at two reductions that will give us more intuition about what is it that makes minimum stable cut hard. So intuitively, the objective of this problem is to partition the neighborhood of every vertex as evenly as possible, because then no vertex will have incentive to join either side to increase its cut. Given this intuition, it's not surprising that we can try to reduce a problem such as three-set splitting to minimum stable cut, because in three-set splitting the objective is exactly to split the vertices of a given hypergraph so that every hyperedge contains both colors of the partition. So given an instance of three-set splitting, we can construct a simple reduction as follows. For every hyperedge, we construct a vertex that's connected to the elements contained in this hyperedge. Now it suffices to add a few leaves to make sure that the original vertices are always stable, no matter what assignment we select for them, and now the new instance we have constructed is essentially equivalent to the original set splitting instance. The objective is simply to make sure that the neighborhood of every new non-leaf vertex contains both colors. Because three-set splitting remains NP-hard even if the maximum degree of the input hypergraph is 3, we obtain NP-hardness for our problem when we have constant maximum degree. Importantly, this reduction works with unweighted instances, so the hardness of the problem here does not come from the hardness of local max cut, which is tractable for unweighted instances. This is a completely different reason why minimum stable cut is NP-hard. Of course, one could argue that it is not surprising that such a problem is NP-hard on instance with bounded degree, because most NP-complete problems are still NP-hard if we bound the maximum degree. So it's perhaps a little more surprising that we are also able to show that the problem remains NP-hard when the input instance is a 3, because most NP-hard problems become tractable when the input is a 3. For this, we have an even simpler reduction from the weakly NP-hard partition problem, where we're given n integers, such that the sum of all these integers is 2b, and we're asked to partition them into two sets with equal sum, therefore with sum equal to b. Our reduction constructs a star and subdivides every edge, so we now have this simple tree that we have in the figure, and assigns the weights given in the partition instance to each individual path connecting the center of the star to the leaf. So now it is not too hard to see that the only way to achieve a stable cut of weight 3b is to produce a partition of the original instance. Even though these two reductions confirm the intuition that the problem is quite hard, they also give us some indication of what we should look for if we still hope to design some algorithm for it. In particular, the reduction of this slide does not rule out a pseudo-polynomial time algorithm for trees, or more generally for graphs of small tree width, while it's also important to note that the graph we construct has high maximum degree, so it's still conceivable that the problem could become tractable if we say that we consider instances where both the tree width and the maximum degree are bounded. So this is exactly what we're going to do in the next part. Let us therefore present two simple tree-width based algorithms that solve this problem. Our algorithms will follow the same general approach that tree-width based algorithms usually follow, which is dynamic programming. And we can take as an example the classical max cut algorithm, which solves this problem in 2 to the tree width. The key idea of this algorithm is that every bug of a tree decomposition is a separator. Therefore, if we are performing dynamic programming where we have already processed some part of the graph, and there is also some remaining part that we have not yet looked at, it is not necessary to remember all the information about our partition, the partition that we're trying to build, but it is sufficient to remember how this partition interacts with the bug, in particular which vertices of the bug are red and which are blue. This approach naturally gives a complexity of 2 to the tree width for max cut, but unfortunately is not sufficient to get an algorithm for minimum stable cut because there is some significant piece of information that is missing. In particular, For a vertex inside the bag, it is not sufficient to just remember what color does this vertex have, but we also need to remember, for its neighbors in the processed part, how many of them are blue or red. This is important information because it determines whether this vertex is stable or not. We can therefore try to fix this algorithm and to extend it to minimum stable cut in two ways. One is the obvious way, which would say, in addition to remembering which vertices of a bag are blue or red, for every vertex of the bag, I will remember what is its incident cut weight on the processed part towards blue vertices. Now, if the maximum weight of any edge in the instance is W, that means there are only delta times W possibilities per vertex, which gives a dynamic programming table of size delta W to the power of 3 width. Clearly, storing this type of information is sufficient to determine if a vertex is stable, but of course the problem is that this type of running time is pseudo-polynomial and becomes quickly unrealistic if W is very large. So we could also try another approach. We could say for every vertex we're going to store the partition of its neighborhood in the processed part. And since every vertex can have at most delta neighbors in the processed part, that would be 2 to the delta case per vertex, so that would give a table size of 2 to the delta times 3 width. Now it's important to note that there is no clear relation between these two algorithms. In particular, which one is better depends on the relationship between W, the maximum weight of the input instance, and 2 to the delta. So for some instances one algorithm will be faster, and for some others the other algorithm will be faster. What is, however, absolutely clear is that both of these algorithms are significantly worse than the 2 to the 3 width algorithm which exists for maximum cut. This difference is partially justified by the two reductions we saw. For example, someone could say, of course we cannot get a 2 to the 3 width algorithm for minimum stable cut, because the problem is weakly NP-hard trees. Nevertheless, one could hope to get a 2 to the 3 width times some pseudo-polynomial time algorithm, while what we're getting here is some pseudo-polynomial time algorithm where the dependence of W on 3 width is XP type and not FPT type. In the same vein, one could pose the question, okay, it's clear why the algorithm has to be exponential in both delta and 3 width, but that would mean 2 to the delta plus 3 width and not to the delta times 3 width. So how is this type of running time justified? So clearly the two reductions that we have seen, which are too simple, cannot answer this type of question, so we'll have to proceed to a more careful lower bound that will indeed justify why these two simple algorithms that we have just seen are actually both optimal. Our main technical result is therefore to prove that these two algorithms are optimal, assuming the exponential time hypothesis. And before we do that, let's just first observe that this is kind of a tricky question, especially for an algorithm with running time 2 to the delta times 3 width. Why? Because there are two variables involved here, delta and 3 width. So it's not clear how to prove that this type of dependence is optimal for any type of relation between delta and 3 width. So someone could consider some algorithm that runs in, let's say, 2 to the delta square times square root of 3 width, and such an algorithm will not clearly be faster or slower than the algorithm we have here. So how can we argue that the algorithm we have here is the correct one? In other words, the technical challenge here is that running times with two variables are not totally ordered. We're going to work around this fundamental difficulty by constructing not just a simple reduction but a parametric reduction, which for any desired value of delta produces an instance with an appropriate value of 3 width, so that the running time of all algorithms matches what can be expected assuming the exponential time hypothesis. An added property of our construction would be that 2 to the delta and W will be polynomially related, and therefore both of the algorithms that we have considered will have more or less the same running time on the instances of our reduction, and both of them will be shown to be optimal. To get a feeling of the parameters of this reduction before we proceed to the actual construction, one can think of a reduction from 3-set splitting which cannot be solved in 2 to the little of n time, assuming the exponential time hypothesis. And what we're going to do is have a construction which for any desired delta, which is super constant but sublinear, produces an instance such that the tree width is also super constant and sublinear, and delta times the tree width is more or less equal to n. If we achieve this, then we're going to rule out the mysterious possibilities of improvement of the previous slide, in particular a running time that is FPT type n pseudo-polynomial in tree width would contradict the ETH, and also a running time of the form 2 to the delta plus tree width, because both delta and tree width are sublinear in n, would also contradict the ETH. So this parametric reduction for any relation between delta and tree width, whether delta is square root of n and tree width square root of n, or delta is log n and tree width is n over log n, or converse, for any such relation proves that the algorithm that we have is essentially optimal. The basic idea of our construction is to revisit the reduction that we already did from 3-set splitting, which constructs instances of bounded degree, and try to trade off the degree with the tree. Now recall that what we're doing was replacing every hyperedge with a vertex, and of course this in general constructs an instance with large tree width, because we do not have any bound regarding the connectivity between the new checker vertex that we added and the original vertex of the hypergraph, which we call the choice part of the instance. Nevertheless, we do have constant degree, so this gives us a little room to maneuver. The idea will be to try to untangle these complicated connections by taking many copies of the choice part and then attaching one checker vertex to each of these. So each of these gadgets now has very low tree width. But of course the problem if we do this, if we make many copies of the choice gadget, is how do we ensure that the solution of the new instance will have to be consistent? How do we ensure that the choice that we make in the first gadget has to be respected throughout the instance? We're going to ensure this by replacing the question marks in this video by some gadget that makes sure that the choices remain consistent, and if we connect all the different copies of the choice gadget in a path-like manner, what will dominate the tree width of this construction is the size of each gadget that replaces these question marks. So the idea is that as the degree increases, as delta increases, the size of this gadget should decrease. In particular, what we're aiming for is that for any given delta, the size of its question mark gadget should be n divided by delta, approximately. Now, given this general description, it is perhaps not that complicated to guess what the gadget is going to be. We're simply going to group delta vertices from one choice gadget and the corresponding delta vertices from the following choice gadget and give them a common neighbor. The only trick is that the weights of the edges of this common neighbor to the vertex to the choice gadget are going to increase exponentially. Now this makes sure that the only way that a stable solution can cut exactly half of the incident weight of this new vertex is if it remains consistent, or more precisely, if it completely flips the choice from one choice gadget to the next. Notice that this simple construction can in principle be executed for any delta, and it will indeed produce a question mark gadget of size more or less n over delta as we promised, so the tree width is indeed going to be n over delta. Furthermore, it's interesting to note that for this particular class of instances, the two algorithms that we sketched are equivalent because storing the weight that this new vertex has to the blue side on the left and storing the partition of the neighbors of this vertex on the left between red and blue are essentially equivalent because the weights are exponentially increasing. So this construction was the last ingredient that proves that both of our algorithms are indeed optimal under the exponential time hypothesis. To conclude, we just explain why the two basic tree-width-based algorithms for this problem, the two obvious algorithms using standard techniques, actually turn out to be optimal. Now, for this particular problem, there is still a lot to be done. In particular, it would be interesting to consider a generalization where stability is not defined only in terms of one vertex, flipping one vertex, but in terms of flipping k vertices for k constant or even for k given input. And it would be very nice to prove what is the complexity of this more general problem with respect to tree width and delta and generalize the results that we gave here. Another avenue, of course, is, as I mentioned, approximately stable solutions, or conversely, solutions which are stable and which approximate the weight of the minimum stable solution. This is wide open. But I think more generally, the take-home message of this talk is that we succeeded to do a very detailed, full-spectrum, two-parameter analysis for this problem. So we succeeded in bounding the complexity with respect to two variables, the tree width and delta, for the whole range of parameters between these two variables. I think this is a nice frontier for parameterized complexity in general. So if you stayed up to this point, thank you very much for listening.